Hello everyone, and welcome to this live demo session organized by Conself. This live demo session, as you may already know, is part of a set of webinars we are going to do and hold in the following days during the autumn of 2017. So there are a number of sessions here. You have most of the dates in which we are holding these webinars and the arguments which is going to be treated by them. To register like you did for this particular webinar, we use Eventbrite, and all the sessions are free. So you're all invited to be part of that and to invite also people and colleagues you may know and that might be interested. Just a small note before we begin the official webinar. It is possible to interact directly with me during the presentation anytime. In fact, you are viewing this webinar using YouTube, and on the right-hand side, if you are signed in YouTube and you click the sign in and you have a YouTube account, it is possible for you to add a comment or to write something on the chat. I will try to reply you live, so without making you wait for extra time. And obviously, I invite you to make as many questions as possible, because that is the best way for us to reply to your needs. A brief introduction of Conself, as you may already read around in our website or in all of the news we spread around. We are a company. We are based in Italy, actually in Milan, close to the airport of Milan. The company has been operative since April 2015, so this is the third year of the company. Our mission is to provide design technology to all the engineers, and we want this design technology to be as easy as possible for everyone. The service we offer is a cloud computing service, so basically directly from the website and with a simple registration, so with a simple email and password, you can access a complete CFD, computational fluid dynamics, and FEA, finite element analysis software. These software are actually based on the well-known open source tools such as OpenFOAM for the CFD part and CodeStar for the finite element part. So directly from the website, it is possible to upload a step file, create a mesh, and run the simulation, and also analyze the results, like we are going to discover today during this live webinar. Some of the customers which are currently using the application are Pedrolo, Micro Italia, and OneWorks. We picked these three particular customers because of the fields where they apply the simulations. The first field is the pump analysis. The second for Pedrolo. For Micro Italia, instead, we have fire scenario simulation in car park loft. And for OneWorks, we have building simulations, so city and pollutant distributions in a city. But also we have wind pressure on these buildings analyzed to calculate the structure of the building. So now we are entering a little bit more into the details of today's webinar, and we are going to discover how you can simulate a simple impeller using Conself. I added here 2 or 3 pictures just to make as clear as possible the simulation we're about to run. This on the left-hand side, it is an impeller. As you already know, it is a particular tool that through a rotation, which is actually occurs along the vertical axis in this picture basically creates a suction force for the fluid, liquid, water in particular, and this fluid, because of the centrifugal force, goes through the channel and goes out radially through the impeller, so all over the radial directions. This is a complete impeller, but obviously we are just interested into a slice of it. Why? Well, because we can take advantage of the axial periodicity of the impeller, so we just simulate 1/8 of the total impeller, so just part of the total impeller, in order to save computational power, in order to be as accurate as possible with the least amount of cells possible. At the same time, here in red is highlighted the fluid volume. In fact, the solid volume over here, the material body, is not of interest in case of a CFD analysis. We just want to draw the negative of it, and this must be done previously using one of the 3D modeling software you might have available, or using the 3D modeling software Onshape, which is one of our partners. This particular, let's say, red zone is here reported, divided by the surfaces, and in particular taking into account the physical behavior that is happening on each of these surfaces. We have in red here at the top of the inlet surface, the suction surface from which the flow is sucked from the pipe upstream the impeller. Then we have here in green the outlet zone, so the two surfaces from which the flow exits the impeller. Obviously here in purple on the right hand side, on the left hand side, a little bit hidden because of the curves given by the particular slice, are the two periodicity phases. These two phases are just a way we use in the software to tell, hey, this slice is repeated again and again, and there is a connection between the left periodicity phase and the right periodicity one. Then in gray here at the center, we have a solid wall, actually we call it blade, and then we have the top surface, which is the shroud, and the hub on the other side. We can't see right in this image. This is an exemplification of the simulation we're running right now, and if you want to do it yourself, it is possible to download using the link over here. So docs.conself.com/contributing/downloads. From this website, we're gonna see in a moment together, it is possible to download the geometry we are using today, and so you can actually rerun today's webinar by yourself. So we are moving now, and we are going to see the Conself CFD simulation. So I am now on my own browser. So this is Google Chrome, but you can use any browser you want. To access the application, you have to go under the My Account page. So login, if you haven't done that already, you can actually register by using any email address you want and by defining a password, and click on the big button, Start Your Cloud Simulation. In this way, you're redirected to the website app.conself.com, from which you can actually start the simulations. So today's webinar, it is a simple pump. So I'm about to create a pump, a new case, and I'm naming it pump. The new case uses the CFD Turbo single reference frame application. So I click on the create button. Sorry, I did it wrong. So I just retype pump and reselect the application and click on create. After the page loads, here it is, I am redirected to a guided procedure from which it is possible to define the simulation. The first thing we have to do, obviously, it is to upload the file. As I said previously, we're going to use our manual to download the file to our local machine and re-upload it to the system. So we use downloads, and over here there is a number of files available to users for their own tests. And this time we use the Impeller fluid.stp file. So we just simple click it and it is downloaded now to my system, to my computer. So from here now I can upload this file. So I just go to download, Impeller fluid, open. Most of the time step files are rather small in size, so the upload procedure won't take a long time. So this is the Impeller as we saw previously in the presentation. The first thing to do in Conself is the definition on the surfaces group as we saw earlier. So we just click in here on the top surface, it becomes red, and we can create this, and we define that to be an inlet. We click on the outlet surfaces. Then we have the two periodicity surfaces, so we call them perio, one on the left hand side, and create boundary perio 2 on the right hand side. So we have also the blade at the center of the impeller, and the top and bottom surfaces are instead hub shroud. So now the full geometry is defined, so there are no more free surfaces to define, and I can proceed with the guided procedure to set up the simulation. So I simply click on the information tool to know the bounding box, so the maximum dimension in X, Y, and Z, as you can see, is 107 millimeters in Z direction, so I leave the file units to be millimeters. I can proceed with the definition of the flow type, and in this way, in this particular app, I just have only one option available, so there's nothing big to say. I click submit and I press IM. As you can see, the process now runs in background, and the process actually does not run on my own computer, but it is performed on Conself server. So all the computing power required to run the CFD or the finite element analysis is taken from Conself, is actually rented by the user, and as we are going to see later, the pricing schemes actually takes into account only the computing power used by the user in a sort of pay-per-use system. Before we proceed, I would like also to mention the support available on Conself, which is live because you are uploading the file to Conself system, and basically you can have a certain number of supports. The easiest way is by using the contact support button here on the left hand side, and automatically you have a support request form in which you can ask the Conself support team for help. At the same time, Conself monitors the system 24/7 and always gives hints, a number of hints to users according to the problems they experienced during the simulation. In particular, have a look also at the user manual, which we quickly saw before to download the files, but actually gives you a high number of hints and a high number of guided procedures to deal with the problems you might have during a CFD or a finite element simulation. All right, this step, it is taking a little bit, so we're going to use a previous prepared simulation to run to see what's going to happen after the geometry. So I just open it. After the geometry, what we have to define is actually the mesh. What happens over here is that I have the geometry available as specified in the previous simulation, and step by step I have to define all the input parameters to define a mesh. Obviously, the first parameter is the meshing algorithm, which for this particular case, which is related to single reference frame rotating pumps, we just suggest to use the tetrahedral meshing algorithm. And then there is a number of parameters such as the uniformity level, which for this case we impose to be 95%. I proceed next with the surface refinement. This surface refinement represents the dimension of the triangles, because you're using a tetrahedral mesh, on each surface, on each group of surfaces actually. So once again, we are required to define a uniform level, always 90 or 95 for our case, and a certain dimension of the cells. We use 1 millimeters on all surfaces. Most of the time, you can actually decide this number to be between 1 centimeter or 1 millimeters for this type of simulations. But I invite you to do some calculation in terms of Y plus to be more accurate and more precise in defining these numbers. So I carry on with imposing the input data we said before, and I move on to the next section. This section is useful to define the boundary layer. This is an extra word refinement, which is very useful when we're to be applied, to be used in all surfaces where we want to apply a wall boundary condition. In our case, the wall boundary condition are going to be applied on the blade. So on this, we apply a certain number of layers and the first cell height to be 1/10 of millimeters, so 0.0001 meters, obviously. But this is not the only wall we have in our simulation. We also have the wall's boundary, which is actually the top shroud and the bottom hub. So on these two solid boundaries, we are applying an extra refinement to be 4 layers of cells, with the first layer to be 1/10 of millimeters in terms of height of the layer. We submit now the mesh, and it is possible to give a number to this, to give a name to this particular mesh. So we call mesh tutorial. Now, when I click IM, automatically the system takes into consideration the mesh which has to run, and here it is. The process actually runs in background. As we can see, it is possible to run a very high number of processes together on the system, and automatically these processes are going to let's say to be simulated and to be processed by our system. Most of the time, the queuing time is rather limited, is, let's say, within 10 minutes, and we have a scalable system underneath. So as you can see later on, all the processes are going to be taken one after the other into consideration by the system. Because of the limited time I have available, I proceed, and we're gonna use now a previously run mesh. So I'm going just to select a mesh which I previously defined, and automatically on the right hand side here I can see once again the impeller, but this time it is not just the impeller, it is the volume of fluid divided into a number of fluid volume, as we can see over here. You need to get familiar with the number of input, but over here, I'm not sure you can see it actually, that we can actually see the layers number, so the imposed boundary layer, so the imposed layers number of cells, and the internal mesh on the inside of the impeller. Well, now that we are happy with the mesh, obviously there is much more to say, like reports about mesh quality, which are actually given by Conself as non-orthofaces, and a number of variables from which you can extract problematic cells out of the mesh. You can proceed with the definition of the fluid model, incompressible, and the turbulence model, which I suggest you to use Spaller-Talbras. But we also have available standard K epsilon and K omega SST turbulence model. I still don't see any questions in the chat, so I can proceed, but I invite you once again to make as many questions as possible. Don't be shy, please. I'll be happy to reply any possible questions you might have on the application. So I can move on and apply the rotation to the impeller. This particular app we are using, it is a single reference frame system. So all the fluid volume is defined as in rotation. So everything we have to define is a center of rotation and a rotational axis, which is the vertical axis in y direction. The rotational speed, and as most of the time for pumps, is about 1,500 RPM here in the EU, where the frequency of the current is 50 Hertz. Obviously, in other countries, this value might be slightly different. We can proceed once again and define the boundary conditions for all of these. So we can define the periodicity rotation for period 1, and once again, we can define the periodicity rotation also for period 2. Then we have the blade, which is a rotating no slip with obviously a 0 rotation. Remember that this 0 is a relative rotational speed. So it is a rotational speed relative to the rotational speed of the fluid volume. Then we have the outlet, from which we just define a pressure outlet. And we also have the inlet, from which we want to apply an inlet absolute velocity to be minus 0.1 meters, so vertical direction inwards, towards, inside of the domain. The last boundary is once again the wall boundary, which represents the hub and shroud, so top and bottom walls, let's say, of the impeller. And we can move on to the time evolution of the simulation. We just want to run a steady simulation. We suggest to run a 1,000th number of iteration and to save every 100 iterations. So we are about to save 10 number of different plots of the solution. Okay, because 100 times 10 becomes 1,000. And then it is also possible to select the number of cores on which we want to run the simulation. The number of cores also defines you the particular machines on which you are running the simulation. So the higher it is, the more RAM you have available. This RAM is important in terms also in case you have a very let's say big mesh, big in terms of fluid element of cells. This, if you click on the eye over here, you can see the total cells number, which for the current mesh is about 650,000 elements. So now we click submit, and once again we can define CFD tutorial. So the name of the CFD we're running, IAM, and here it is. Now the simulation, the CFD simulation is running. As we see now, the system is actually differently from what's happened previously, in which we were on the queue. Now the system has taken into consideration the steps we submitted previously, and automatically it is running them. So we don't actually have to do anything to that. And as you can see, the mesh we submitted previously, it is now completed. And in 1 minute probably, we are also, here it is, the mesh is completed, it disappeared. And in 1 minute probably, also the CFD we have just submitted is gonna be taken into consideration by the system, and it is going to be actually run by our automatic system. Well, as I said before, we move on because we don't want to stay here, but I just want you to see that the system, here it is, that now the status is in running, so it is proceeding now, the simulation has started. So now we want to see the results of the simulation, what we have available in Conself. We just open a new case, the previous run case, we go to the results step, and here it is, we have the same viewer we got used in so far, and it is possible to click on the residual plot. In here I just have run 1000 iterations, and as you can see, all the residuals are going down. We are to a level of 10 to -2. Probably it is worth a while running for a higher number of iterations. And over here, with once you get familiar with the ParaView, it is possible to actually visualize the pressure, so static pressure of the impeller. As we may expect, we have a higher pressure on the outside of the impeller and a lower pressure on the inside of the impeller. So this is a result we are expecting. It is also possible to calculate the minimum pressure and the maximum pressure, obviously. And once you get familiar with that, it is also possible to calculate the total pressure difference between inlet and outlet. At the same time, it is possible to have a view of the velocity field. So probably here we are just at the beginning, so it would take a higher number of iterations to give a more correct velocity field, but already we have quite a quick overview of the velocity field. Just take a note of the periodicity phase from which we have what is going, this phase to be basically coupled with this one. And it is also possible to have an overview at the turbulence inside of the impeller. So with the turbulence, have an idea of the area on which we want to improve the impeller. So probably over here for this particular case. And obviously, it is also possible to have the velocity, but this time not just the relative velocity, so the velocity in the relative system, but the velocity in the absolute system. So more other features are available, such as downloading the results. We currently have 2 different results formats, so the Insight results and also the Fluent results. And at the same time, it is possible to click here to download ParaView, which is the data viewer the open source data viewer we suggest you to use because it's free and it is quite complete to do any sort of analysis you want. But anyway, if you click on Insight Results, automatically here it is. Results Insight are downloaded to your system. It takes few minutes because download usually is relatively quick. And you can use, for instance, ParaView to view these results set. Okay, probably this was a very quick overview of the application, but the intention was to make you aware of the possibilities in terms of simulation given by Conself. Just one more slice with the pricing of Conself. Our pricing schemes is actually based on CPU hours. So every CPU for 1 hour represents 1 credit, and what you actually buy in Conself e-commerce is a certain number of credits. We have several plans. The first and most simple plan is the welcome plan, which is absolutely free and gives you 1,200 credits every year. So with no limitation except for this one, you can actually run simulations and get, let's say, an idea on how Conself platform works. Then, if this number of credits is not enough for you, you can use a higher number of credits with the freelance plan, which is 179 euros per month and gives you 3,000 credits every year. At the same time, there is another difference between the welcome plan and the freelance plan because commercial features such as file downloads are available only for paid plans. So no download is possible and no other commercial features are included in the welcome plan. And then there is the enterprise plan, which gives you even a higher number of credits and also a higher, let's say, gigabytes available, a higher storage space available on Conself. There is no particular difference. There is no difference except for the number of credits between the freelance and the enterprise. So no feature is, let's say, limited in the freelance with respect to the enterprise plan. Also, for bigger companies, we also have a pay-per-use license. We call it unlimited, from which you must contact us. We advise you to contact us and to give us the chance to give you a quotation for your particular need. This is everything for today's webinar. No questions for the moment yet. So I invite you to register probably to the next webinar. The next English webinar is towards the mid of October, and it is about a finite element analysis of a flange. So we switch to the other capabilities of simulation available in Conself. Instead, we also have webinars in Italian, because we are an Italian-based company and they are quite requested as well. And the next webinar is in 2 weeks' time, towards the end of September. And it is also in this time the webinar about the flange finite element analysis. The registration to the next events, like you did for this one, is through Eventbrite. So you just have to go to conself.eventbrite.com and register to the event you might like. With this is everything for today. So I thank you all for being part of this live webinar, and I'm looking forward to meeting you to the next session. So hello everyone, and talk to you soon. Bye.